Without intermolecular forces, we wouldn't have solids and liquids at all. They're also responsible for some other properties that we observe, and one of these is surface tension. We have a picture of a paper clip floating on water. Paper clips are made of metal. We don't expect metal to float, right? Here is a fishing fly, a trout fly, floating on the water. Its density is greater than water, and yet it floats on the water. And it's the surface tension that does that. Here we can see that the water seems to be sort of bent. It's almost like it's sitting on a skin, or maybe there's a thin cover on the pool and the paper clip's on top and it's just pushing it down. But it's actually just the water itself that does that, and it has to do with intermolecular forces. Surface tension is the tendency of liquids to reduce their surface area. So they can quantify it. It's the energy required to increase the surface area by a specific unit amount. If you're interested, water has a surface tension of 72.8 millijoules per square meter. That probably means nothing. But the surface tension allows trout flies to float, even though the hook is more dense. It allows water bugs to skate on the water. You can float paper clips or needles on water. And I'm sure some of you are going to go home and try that, and you should. How does this work? Well, let's look at this illustration of a liquid, and what we'll see is that the molecules that are inside, in the interior, have interactions in all directions. And the molecules on the surface interact only with their neighbors to the side and their neighbors below. In this illustration, we've got 6 interactions for this guy and 4 interactions for the surface. So the molecules on the surface have higher potential energy. They're less stable because they have fewer interactions. And so if we want to increase the surface area, we're going to have to move some of these interior molecules to the surface. We're going to have to disrupt some of these interactions. We're going to have to raise the energy. And so it's not going to want to do that, because that would be a higher energy state, and everything goes to lower energy. To minimize the energy, liquids minimize their surface area. And the sphere is the shape that has the smallest surface area for its volume. And that's why water droplets are spherical. The surface tension depends on the strength of the intermolecular forces. If those forces are very strong, the surface tension will be great. If the forces are weak, the surface tension will be less. Let's go back to this picture for just a minute. If you put something on top of the water, like a paper clip, in order for it to sink, to break into the water, it's going to have to increase the surface area of the water. And the water doesn't want its surface area increased. It requires a certain amount of energy to do that. And so that's why the paper clip doesn't sink. This is a neat picture taken in space. That's a ginormous drop of water. And you can see that it's pretty much spherical in shape. So water droplets, small ones, are nearly perfect spheres. Larger ones get distorted by gravity. You know, we're familiar with that the teardrop shape, right, of water hanging off of a faucet. It's being distorted by gravity pulling on it. But if you watch high-speed pictures, you see that as it breaks loose, it fluctuates around a little bit, but then it'll go into a more spherical shape as it falls. Any questions about surface tension? You can mess up the surface tension of water by adding something to it, like a little bit of soap or some alcohol. And so if you have, your paperclip, if you were successfully floating your paperclip on the surface of the water and you add a drop of soap, the soap molecules, as they disperse, will disrupt the surface tension and the paperclip will sink. Another property of liquids that's due to intermolecular forces is called viscosity. Viscosity is the resistance of a liquid to flow. It's measured in a unit called the poise, which is a gram per centimeter second. We're not really going to use that unit, but there it is. Viscosity is going to be greater if the intermolecular forces are stronger. So you think about honey, right? Honey is a liquid, but it's very thick, right? And it's difficult to get it to pour. Water is a liquid, but it pours more easily. And then you think about something like alcohol or gasoline, which seems somehow thinner and more fluid, right? It has less viscosity. The viscosity also depends on the molecular shape, because molecular shape affects the intermolecular forces. If we look at these different hydrocarbons, pentane, hexane, heptane, octane, and nonane, we see that their molar masses increase with their size, and we see that the viscosity increases. So we have larger molecules, which means that these are all nonpolar, so they just have the dispersion forces. Dispersion forces are stronger. But as these molecules increase in size, they're also getting longer. And they're like long pieces of cooked spaghetti. And so they have the opportunity to get tangled with each other and to have more interaction on their surfaces because their surface area is larger, so that they can become attracted to each other more. Viscosity depends on temperature. At a higher temperature, the particles have more energy, and so they're going to break free from their intermolecular forces more easily. What happens when you heat up honey? Does it get thicker or thinner? It gets thinner, it gets runnier, right? You heat up maple syrup. It was really thick, and it gets thin and runny. If you take maple syrup and you put it in the freezer, it gets really thick and sticky and hardly will pour at all. So the viscosity depends on temperature. Viscosity in everyday life, we most often hear about in terms of motor oil. The oil in your engine needs to coat the moving parts and provide lubrication. If the viscosity breaks down, if it loses its viscosity and becomes too runny, it just goes to the bottom of the engine and it won't stay on the surfaces that it needs to stay on. And so you want the viscosity to be just right. If it's too thick, if it's too viscous, then it's going to cause problems with the moving parts. So modern motor oils are really, really pretty cool. So they've got polymers in them that will coil up at low temperatures and unwind at higher temperatures, because the viscosity of the oil depends on the temperature. So when these polymers coil up and become more spherical, their surface area where they can interact with other particles decreases and the intermolecular forces get weaker. That contributes to less viscosity. That counteracts the temperature dependence, where at low temperatures, the oil becomes more viscous. So that counteracts that. At high temperatures, the oil becomes less viscous, and that can be a problem. These polymers uncoil at the high temperatures, increasing the surface area, increasing the strength of their intermolecular forces, and counteracting the viscosity decrease. And so I just think that's really cool. Science applied to your car engine. Here we look at the temperature dependence of the viscosity of water. It has a viscosity of 1 at temperature 20 degrees, and as we increase the temperature, the viscosity falls. Capillary action. Capillary action is the ability of a liquid to flow against gravity up a narrow tube. So if you stick a tube, very small diameter, into a liquid, water will just run up it. That doesn't happen with something the size of a drinking straw. It has to be something very narrow. And this is due to the combination of two different forces. There are cohesive forces and adhesive forces. Cohesive forces are the attractions between molecules in a liquid. Adhesive forces are the attraction between the liquid and the surface of the tube. If the adhesive forces are stronger, the liquid will rise up. If the cohesive forces are stronger, the liquid will not rise up. And so here we're seeing a difference in levels due to a difference in the diameter of these tubes. A more narrow tube, the liquid will rise higher than in a larger diameter tube. Here's a test tube with water, and we have this familiar concave meniscus. The meniscus curves down. That's what most liquids do. And this is because the adhesive forces are stronger than the cohesive forces, and so it bends up a little. The water is climbing the glass a little bit instead of just being flat. Mercury does the opposite. It's convex. It bubbles up in the middle because the cohesive forces between the mercury atoms are greater than the adhesive forces between the mercury and the glass itself. You can see a different shape of a meniscus if you use a different type of material. If you use plastic, we have some plastic graduated cylinders, and the meniscus is much flatter in those because the water is not as attracted to the plastic as it is to the glass.